Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is accumulators. Our objective is to examine an extremely handy peripheral hydraulic component known as accumulator. Accumulators perform numerous important functions in a hydraulic system, including, but not limited to, maintaining system pressure when several components activate at the same time, developing fluid flow, compensating for thermal expansion and contraction, controlling noise, or absorbing shocks, surges, and spikes in pressure, maintaining pressure in the event of pump failure, allowing the orderly shutdown of a system, smoothing pump pulsations, and compensating for fluid leakage. Despite these numerous important roles, accumulators are astoundingly simple devices. Accumulators are basically a tank of pressurized fluid placed close to vital points in a circuit that require pressure and flow to ensure stable, reliable operation of the system. Accumulators are hydraulic energy storage devices designed to meet momentary pressure and flow demands. Accumulators are generally divided into two classes based on how the accumulator maintains force on the stored liquid: mechanical and hydro-pneumatic or gas-charged accumulators. Mechanical accumulators are further subdivided into those that use springs and those that use weights to pressurize fluid. A spring-loaded accumulator applies force to a stored liquid by means of a spring acting on a piston. If fluid pressure drops, the spring returns to its expanded state and returns energy to the system, thereby stabilizing its operation. Similarly, any pressure spikes or surges can also be absorbed by the spring, quite like a shock absorber. Sometimes spring-loaded accumulators include a mechanical stop that prevents the highly pressurized system from overcompressing the spring and damaging the accumulator. A weighted accumulator swaps out the spring for a large block of concrete or metal. For obvious reasons, weighted accumulators must be mounted upright and are not suitable for all applications. One of the advantages of weighted accumulators is that they exhibit constant predictable force throughout the discharge cycle, whereas a spring-loaded accumulator exerts nonlinear force as a function of the spring compression rate. Both these types of mechanical accumulators may include a vent port on the weight or spring side to drain away any fluid that leaks past the piston. Note the schematic symbol for a spring-loaded accumulator includes a spring, and a weighted accumulator includes a block. The other class of accumulators, gas-charged or hydro-pneumatic accumulators, use compressed gas to exert force on a hydraulic liquid. Gas-charged accumulators are categorized by the barrier used to separate the compressed gas from the liquid, either a piston, a diaphragm, or a bladder. There is only one schematic symbol for a gas-charged accumulator, regardless of construction, that of the base accumulator symbol with an empty arrowhead. A piston accumulator consists of a cylinder sealed by a gas cap with a charging valve on the gas end and a hydraulic cap at the hydraulic end. A lightweight piston separates the gas side of the accumulator from the hydraulic side. A diaphragm accumulator swaps out the piston barrier with a flexible synthetic rubber disc between the top and bottom halves of a spherical vessel. As pressure changes, the disc distends and supplies or absorbs pressurized flow. Finally, bladder-type accumulators use a strong synthetic rubber balloon to exert and absorb pressure. Bladder accumulators often include a poppet valve that closes when the accumulator is fully discharged of liquid to prevent the bladder from extruding into the system. Additionally, bladder accumulators often include a top opening, allowing a technician to remove and replace a damaged bladder after the system is locked and tagged out. Similar to spring-loaded accumulators, all three types of hydro-pneumatic accumulators exert nonlinear force throughout the discharge cycle since they are an interaction between an incompressible liquid and a compressible gas. All three types of gas-charged accumulators necessitate a manufacturer-recommended precharge prior to being used in a hydraulic system. Precharge is the pressure of the compressed gas prior to the admission of fluid. Not just any gas can be used for a gas-charged accumulator. Dry nitrogen is the gas of choice because it is inert, meaning chemically stable, and in contrast to air mixed with hydraulic fluid vapors, has less of a tendency to explode. Always a desirable characteristic. Always charge gas accumulators with dry nitrogen or another inert gas and follow manufacturers' recommended procedures when doing so. We'll discuss precharge pressure and its influence on capacity in a moment. As an example of an application befitting an accumulator, consider this simple circuit consisting of a hydraulic double-acting cylinder that is extended only infrequently. However, when required to do so, must meet stringent speed and force demands. Lacking an accumulator, the pump must be oversized for this peak demand, and when the cylinder is idle, is essentially wasting energy. An accumulator and check valve positioned ahead of the directional control valve changes this dynamic. Consider a very small displacement pump that gradually charges the accumulator over the lengthy idle period. When time comes for the cylinder to extend, the accumulator makes available a sufficient quantity of pressurized fluid without the use of an expensive, oversized high-power pump. The accumulator therefore serves to develop fluid flow by spreading out the demand over time. Note accumulator circuits may feature flow control valves with check valve bypasses on their fluid ports. Note the orientation of the flow control valve with check valve bypass suggests that while charging, the flow control valve is essentially bypassed, allowing the accumulator to charge as rapidly as the pump is capable of doing so. In contrast, when discharging during the act of extending or retracting the cylinder, the orientation of the flow control valve with check valve bypass suggests the flow control valve is not bypassed, and the flow control valve regulates the rate at which the accumulator is discharged. This same circuit can be used to demonstrate another important accumulator application, that of maintaining pressure and sourcing flow during emergency shutdowns. Lacking a source of pressurized flow, an actuator would be essentially helpless to contribute toward any orderly shutdown of a system. In the event of pump failure, note that the check valve in the pressure line prevents accumulator bleed down. The stored liquid under pressure can be used to extend or retract the cylinder a finite number of times with a progressively diminishing amount of force as the accumulator is discharged. Desired pressure, flow rate, actuator size, and cycle count must be taken into consideration when sizing an accumulator for this application. An example necessitating a backup source of hydraulic power would be the hydraulically pitched blades of some modern horizontal axis wind turbines. Pitch control systems in wind turbines continually monitor and adjust blade angle to ensure maximum power delivery, at the same time preventing dangerous overspeed conditions. In the event of pump failure, the stored energy in the accumulator can be used to rotate the blade back to the safe position and aerodynamically brake the rotor. Another example might be using the stored energy in the accumulator to actuate a brake without reliance on a pump. The accumulator must be sized to account for the required braking force and holding time. Note, as illustrated, this system would necessitate electrical power to actuate the solenoid-operated directional control valve to actuate the cylinder using the stored energy in the accumulator. For this reason, systems designed to undergo orderly emergency shutdowns must also include an uninterruptible power supply to power the control electronics that make this possible. We'll discuss hydraulically pitched wind turbines and braking applications in later lectures. Even without worrying about emergency shutdown scenarios, the accumulator in this same circuit can also be used to limit runtime of the motor-driven pump. Again, consider an actuator only infrequently used, for example, a hydraulically applied brake. Only when actively extending or retracting does the cylinder require flow. Otherwise, it can be placed in a static idle position. During idle time, the pump can charge the accumulator, and when pressure has reached a predetermined value, as dictated by the set value of the pressure switch incorporated on the pressure line, the pressure switch can be used to turn off the motor-driven pump. This prevents the pressure relief valve from being actuated and the motor-driven pump from being run, both scenarios essentially wasting energy. If pressure in the accumulator drops to a leakage, or if the actuator is being called into service, pressure would fall below the reset value of the pressure switch and turn the motor-driven pump back on. The accumulator and pressure switch combination therefore keeps pressure inside a given range between the set and reset value of the pressure switch and limit the runtime in the motor-driven pump. Ordinarily, the system would simply run off the charged accumulator, and the pump's only purpose is to keep the accumulator inside this given range. We'll examine unloading valves and differential unloading relief valves, as well as motor control circuits making use of pressure switches and more in later lectures. But wait, that's not all. Accumulators can also be used to compensate for thermal expansion and contraction and absorb shocks. Consider this system being used to actively compress a mold. As the hot molded piece cures, heat can cause liquid in the cap end to expand. Without the accumulator, pressure could rise to the point of component, fitting, or conductor failure. With the accumulator in the circuit, the excess volume from the expanded fluid can be absorbed, thereby keeping pressure relatively constant. Accumulators can also absorb shock caused by fluid inertia. Consider a high-volume pump cranking out a large quantity of flow. When the directional control valve shifts to the closed center position, this huge quantity of flow slams to a stop, resulting in a pressure spike throughout the system that can damage or destroy it. An accumulator, however, would absorb and reduce the shock effects of the fluid inertia. Finally, consider this extremely simple clamp and bend circuit consisting of two directional control valves, DCV-C and DCV-B, controlling two separate cylinders that respectively clamp an object and then bend the clamped object. Consider a scenario in which the clamp cylinder is actuated first. During the act of extending the clamp cylinder, pressure would be relatively low since the system only needs to overcome the friction of the piston on the barrel and fluid resistance. Once the clamp cylinder reaches the limits of travel on the workpiece, pressure would begin to rise. The object would be securely clamped at some point. If the system moved DCV-B into the straight-through position, one could expect pressure to momentarily drop while the bend cylinder is extending, potentially dislodging the clamped workpiece. Given one of the principal roles of accumulator is to maintain system pressure when several components activate at the same time, an accumulator placed in this circuit supplements pump flow when flow is being diverted to the bend cylinder, making available a quantity of pressurized fluid when the circuit most needs it, thereby keeping the workpiece clamped. Note the check valve on the pressure line of the clamp cylinder maintains the pressure and force in the clamp cylinder while the bend cylinder extends. Only when the bend cylinder makes contact and starts bending the workpiece does pressure begin to rise. We'll examine more sophisticated clamp and bend circuits in later lectures, making use of a pressure control valve known as a sequence valve to automatically ensure the clamp cylinder clamps the workpiece first and then bends it, not the other way around. Additionally, we'll examine electrically sequenced hydraulic circuits making use of limit switches and ladder logic to coordinate the clamp and bend sequence.